Yeah, they're going to be late, so I think we're just going to start.
Yeah, crack on. Okay, good. So there's one structures presentation this week. I'm going to be talking about what I've been doing for the past week. So presentation will go as follows. Initially I'm going to talk about the scope of my aspect of the structures side of things. I'm going to talk about my approach to solving the problems at hand. I'm going to briefly talk about the preliminary results that I've obtained from some of the analysis that I've done so far. Highlight some issues and some solutions for them. And then talk very briefly about how this integrates with what Manhart and Carlos are doing, who are the other members of the structures team. And finally, an idea of how I'm going to move forward from here. So, the scope of my side of the structures thing. Well, really, I'm doing the fuselage and the hull structural design. So this will entail getting information from the aero team on the aerodynamic form of the hull, and then putting that together and making sure that that can withstand hydrostatic, hydrodynamic loading, bending moments, torsion, shear forces, all this kind of stuff. So really, it's quite a big, it's quite a big task. So I've broken it down into sections so that I can approach it in a way which makes it more solvable. In brackets at the bottom, I've got integration with additional components. So this kind of covers integration with the propulsion systems that we've got, which are sort of mounted on the fuselage for the air, for both the water and the air components. They're both integrated within the fuselage to a certain extent. So that will require some analysis and reinforcement of the various parts. So where to begin? Well, hydrostatic pressure calculations is where I decided to kick off. So this thing has to travel some depth, between 30 and 40 metres below the surface of the water. So there's going to be some significant, reasonably uniform pressure loading on the hull to begin with. And I've looked at modelling this as a simple cylinder just to get an idea of what sort of skin thickness we might be dealing with. So what I've taken is some information, some equation from Rourke's stress and strain book, which is wonderful. And I've taken these formulas for the uniform lateral external pressure loading on a cylinder of a defined length. And the length of the cylinder that I've taken is essentially the length of a fuselage, if you like, between two frames. Now the frame spacing I've chosen to be 0.5 of a metre, and this is just an initial choice, and it's actually based on, I've looked at both submarines and aeroplanes, and by and large they're almost exactly the same, and they vary very little between the two, so it always seems to be about half a metre. So I've taken half a metre to begin with, and this might be something I'll optimise later, and I've looked at uniform loading on a cylindrical shape, put the details into Excel so that I can change materials and stuff, and I've come out with 12 millimetres of skin. It's the point at which elastic buckling won't occur under the pressure loading of about 500 kilopascals, which is the pressure at about 40 metres depth, which is the top end, I imagine, of the depth that it will be reaching. Of course, this doesn't take into account placement of stringers along the length of the fuselage at all. So in reality, what we're going to be looking at is a slightly different case, where instead of an entire cylindrical shell, it's actually just going to be perhaps a series of curved plates. And this is, again, an idealised model where I've assumed that both the frames and the stringers are rigid, and I'm looking at deformation only of a section of curved plate. The dimensions of the plate, again, depend on the frame spacing and the stringer spacing. So what I've done is I've put these two formulas again into Excel, and this one is for simply supported edges, and this is for edges which are clamped. Now the clamped edge case is a little more complicated, but probably more applicable, seeing as these plates in essence are going to be bonded to the stringers. So when I've run the calculations on this, this aluminium alloy comes out to somewhere between 5 and 6 millimeter skin thickness to avoid elastic buckling. The 6 millimeter is if it's simply supported, 5 millimeter is if it's clamped. There are a lot of assumptions that have been taken into account there, and one of them, and probably the most prominent one, is that it's assuming that the hull is cylindrical in shape, and in reality it's not. As you can see up here, the hull that we'll probably be choosing is from, well, it's going to be chosen by the aero side of things, but it's actually from a study done by NACA on the aerodynamics of hulls in water, and the shape of which is a little bit more complex. So what I've done is I've taken these sections, I've used a graph digitizing program to allow me to take coordinates from each of the sections, put this into Excel. I've written a macro script so that I can easily scale these sections up and down to change the dimensions of our fuselage, and output the file to an IDL which can be imported very easily into Pro-E. That allows me to model the fuselage that will be taken quite quickly. And from that, I can then take different sections of it, import it into Abacus, apply a mesh, apply some loading. External pressure loading is what I'm looking at the moment, as until I get some further information on the aerodynamic loading side of things, I can't really look at bending or torsion or anything else. So yeah, I've done this, put it in Abacus, and apply the worst case scenario loading. Now, the deformations here are actually a little bit hard to see, but you can see that the highlighted areas are really where the stress concentrations exist. Now, there's no scale at the moment that's really applicable because sizes are changing, so it wouldn't really make that much sense. But this gives me an idea of where the concentrations of stress exist. And as you can see, on any surface which is concave, unsurprisingly, has greater stress concentrations. So the really key areas are going to be where the hull, the fuselage, goes from convex to flat, and then the concave part on the keel are going to be areas which I'm going to have to look at in further detail to make sure that it can withstand the pressure loading at the depths that we'll be looking at. So briefly, some problems that I've got so far, and some problems that are ahead of me, and some solutions that we're going to look at. As I've said already, skin stress concentrations. Well, this is something that I guess one solution is to increase the skin thickness, although that will contribute to quite a great increase in weight, and perhaps a better way of dealing with this issue would be to use frames which have greater reinforcement and are bonded to stringers which are significant enough to prevent this sort of local buckling that we're going to have in the sections between frames. I might just add that this Abacus analysis that I've done here, actually, obviously there are no stringers in this particular example, so there's no constraints, and this section is just free, if you like, other than the clamped edges, whereas stringers could be idealised as perhaps splitting this into smaller plates, if you like, which perhaps would exhibit much less buckling. Other problems that I've got to solve, well, the integrations with the wings and the engine. This will require so-called heavy frames at the point where the engines and the wings will meet the fuselage, so they'll have to be of a thicker design than probably the rest of the frames in the fuselage. Again, integration with the hydropropulsion. Well, hydropropulsion is actually going to be mounted on the bottom of the fuselage. They're going to need a significant water intake, I think 0.4 of a metre squared or something. So I'm going to have to think carefully about how I'm going to integrate that into the fuselage without compromising structural stability. Moving forward again with my side of things, so I'm going to look at frame sizing next, stringer sizing as well. That will hopefully be something I can look at as soon as I have the aerodynamic bending moments and things. And also something I'm going to have to bear in mind the whole way through is material selection. Of the analysis that I've done and a study that I read, which I think NACA did, on carbon fibre airframe versus, for example, versus a full aluminium one, they're looking at about 70% of the weight if it's CFRP versus that of the traditional aluminium alloys. So that's something to bear in mind if stability tell us that we need less weight, more weight, or different distributions thereof. So yeah, and just quickly just to run through, moving forward, hopefully Aero can give me a hull in the next week, so I'll have exact shape of what I'm dealing with. I can then do a full CAD skin design, break it up into Abacus like I've done before, do some more loading calculations, design the frame. Obviously I need the pieces that I've talked about so far for propulsion, the hydro and air side of things, stability and systems for landing gear placement. That will give me an idea of which frames need to be reinforced. I can then move on to stringer calculations and design, integration with the tailplane and wings. That's the side of things that Manhar and Carlos are dealing with. Hopefully at that stage we'll have more or less a full fuselage which we can do a full analysis on, and then move forward to optimization a couple of weeks from now. So that's everything. Any questions?
Do we clap? No.
Yes.
Good progress, yeah. But I never believe somebody else's Subaru simulation unless I know every single number goes in. So can you explain this?
Yeah.
What are you doing there? Which elements are you using, for example?
Right. So this is all default parameters within Abacus. So the elements, I think, hex elements. Is that right?
So solid elements.
Yeah.
Rather than shell elements.
Solid. Yeah.
What I mean is, across the thickness of the fuselage, do you have more than one element?
No, single element.
So you have only one.
Yeah.
And it's a brick element.
Yeah.
Yeah. Okay. So you cannot believe any of that.
Okay.
Because I'll explain. So the loading is what is pressure.
Yeah.
From the bottom only.
No, across all surfaces, because the whole fuselage is going to be submerged.
Okay, it's very simple, because that thing is going to have a tendency towards bending, and bending gives you gradient of strains, which is a linear gradient along the thickness.
Yeah.
If you have one single element, which is also constant stress element, your analysis cannot possibly capture any bending moment there.
Okay.
That analysis can only give you a constant stress across one element, right? So if you have one element across the thickness, you're never going to get the gradient. Yeah. So there are two solutions. Either you put 10 elements at least across the thickness, but then your number of nodes is going to go up by big times, or you switch to shell elements. Have a look at what they are. They're basically the extension of beam elements for two-dimensional curved plates.
Yeah.
So your degrees of freedom would be displacement and rotations at the two ends.
Okay. I mean, this is all very useful information. In my defence, we've only had a very, very simple treatment of Abacus so far, so I'm kind of learning this as I go along.
Yeah.
But perhaps I'll come and speak to you in
we
greater
need to
detail
speak,
about
but it will take you a second to change it and run it again.
Yeah.
Then, if I understand correctly, on the two cross sections, say, of that thing, you block every degree of freedom, right?
Not every degree of freedom.
So only the axial direction.
Yes, that's right. Yeah.
So you have one element. So effectively, it's clamped.
Yeah, it's essentially like a clamped. I've assumed. Well, yeah. In fact, no. It's 3 degrees of freedom that I've blocked because I've assumed that I've got rigid frames at either end, and it is quite an idealisation. It's not strictly true, but I've assumed that the frames are structurally significant in the sense that they would.
So infinitely rigid frame, and you're looking at
basically yes.
Just the plates. Okay. And then you showed formula from Rourke Young.
Yeah, there are two.
Yeah, exactly that. So, what's Q prime is the pressure that gives you buckling.
Yeah, Q prime is the external pressure. Actually, it's unit loading which gives you, or should I say, per unit length, which gives you buckling.
Okay. I mean, I need to go and look in the book. The problem I have is that I don't think that structure that is sketched there can possibly buckle unless it's an arc of parabol.
Well, it's only
I'll explain.
clamped. It's only clamped at the lengths A and B. So
Because it's curved,
mm,
the application of that load is going to give you a distribution of bending moment.
yeah,
So that thing is going to try to change its shape. The buckling is something else, it's an instability, right? You have a straight rod that can do two things. It can either deform as a straight rod or at some point snap into configuration where it deflects laterally. Whereas I think that structure over there cannot snap. I'm sorry, that's maybe too much. We can talk
yeah,
offline.
yeah.
So is it,
Why can't,
does it refer to a buckling load?
Yeah, it does.
Right.
I haven't got the full book on this piece, but I'll show you afterwards.
Okay, are you sure it's not an arc of parabola that thing? No.
Yeah, I'm pretty sure.
Wait,
I could be
no,
wrong,
sure.
but we'll
Yeah,
have a look.
that's right. Okay, fine. Yeah.
I
Yes.
have a question and a comment.
Yeah.
What's your pressure loading? Are you accounting for the gradient in hydrostatic pressure? Or are we putting
What
it
across the
from top
fuselage?
to bottom of the fuselage?
Well, actually, I'm at the moment no. I'm taking the worst case scenario, which is like full loading at 500 kilopascals, which is at 40 meters. In fact, the Abacus
well, I
analysis.
mean, regardless of what the worst case scenario is in terms of depth, you should still have a gradient in pressure.
No, I understand that. The constant loading that I took was the analysis of this, which is the curved plates and the cylindrical tube, which are not really the formulation of the hull anyway, and it was just to give me a general idea of what sort of thicknesses I'd be looking at. The loading that I did in Abacus was hydrostatic loading, where I defined a zero pressure depth and a pressure depth at which it was my defined loading of 500 kilopascals. So in that sense...
And then you just impose a uniform pressure on everything.
That's right, I assumed that it was just straight and level underwater.
Well, but even if that's the case, because you're...
Well, no, it wasn't uniform pressure, sorry,
Yeah.
it's hydrostatic pressure. So
It is hydrostatic pressure.
yeah, so
you-
Abacus
okay,
automatically takes a
Okay, right.
pressure gradient,
Okay.
if you like.
And then a comment is, why have you done everything in Excel? Would it not make more sense to put everything into MATLAB? That's much more
Yes and
variable.
no. In
I
some...
mean, yes.
yeah, okay, yeah, fine.
just in terms of making things easier for you, because then you can...
I suppose I'm
change anything.
familiar with both. Really, it's just because I had part of the code which allowed me to output our IBL files from L2 last year, so to streamline workload, I decided just to use that. But yeah, MATLAB is probably a better, more professional solution. Not really professional. Any other questions? No? Sweet.